Okay, so thank you for joining us today. Today we will talk, my friends from Lenovo and I will talk about something on AI, deep learning, heterogeneous computing, accelerators, as well as how to use OpenStack and Cyberwar to save lives by detecting heart disease. This presentation will be have two parts. First part was I will talk about Cyberwar's mission in democratizing AI. And then my friends from Lenovo will talk about the heart disease detection and using deep learning. And AI nowadays, AI is everywhere, like autonomous driving, image recognition, even playing StarCraft. People always wondering what AI can do and how it can transform our lives in every way. But as a cloud engineer, I also ask myself what I can do for AI to make it even a better things for us, right? What we can improve AI. To answer this question, we need to identify what's the challenge for AI nowadays at current stage. Look at this graph here. So the red line represents the trend of Moore's law over the last decade. Can anyone take a wild guess on what this blue line represents for? Just guess. All right, so the blue line is the number of papers that have been published over the last decade on AI and machine learning. That tells you how hot AI is and how rapidly it has been grown since then. But having all of these AI capabilities, can we take them out of the ivory tower and make it accessible for everyone, for all, like end users, developers, operators? Like, the answer is the cloud, is using the cloud. And this methodology, we call it democratizing AI. But it cannot be truly done without an open infrastructure for the cloud. We have different AI applications running on the cloud on various frameworks like TensorFlow, MXNet, PyTorch, Caffe, all those stuff. And the cloud providers need to provide the proper infrastructure capabilities for these workloads. Furthermore, on top of the traditional AI, like cloud infrastructure consisting like your PaaS and IaaS resources like CPU memories and the traditional stuff, AI workload requires specialized hardware, which we call domain-specific hardware or domain-specific architecture hardware or DSAs. So what is DSA or domain-specific architecture? This is a word from computer architecture world. It describes a piece of hardware that do only a small set of things and do them very, very well. For instance, neural network processors for machine learning. Example is the TPU from Google. And we also GPUs, which we use to do a lot of the training and inferencing, as well as FPGAs, which you can load your customized logic on it to accelerate, for instance, your network functions and just pretty much anything you can think of. But what's still missing in this picture? Having all of these DSAs or hardwares, we're facing fragmentation problems because every single piece of hardware, they're doing very small things. And unlike a CPU, it's pretty much doing everything. It's a general purpose processor, but those hardwares, those TPUs, NPUs, they're just doing a small set of things, and they do it on their own way. And this creates a fragmentation. And then we also have domain-specific languages running on top of it. Basically, they are the TensorFlow or Caffe that developer uses to write their models for AIs, right? So, and then we need an ecosystem to bridge all of these things like cloud, DSA, and DSLs. But to bridge them, what's the gap, right? What's the we need to know what the gap is before we can even do the bridging. So look at this graph here. On top is the various machine learning frameworks nowadays, like very popular out there, like Caffe, PyTorch, TensorFlow. And at the bottom, we have all different hardware from different vendors, NVIDIA, ARM, Qualcomm, even Huawei just publishes their own AI chip early this year. And this creates a log and square pairs. If any, like for instance, if any vendors wants to publish a new device, they need to support all these different frameworks. It's a lot of work. And that brings Onyx into the picture. Onyx is a open source project pushed out by Facebook and Microsoft. It basically creates a abstraction layer between the top and bottom. Now if you have a new hardware, you just need to write drivers that supports Onyx so that it will support all the frameworks that Onyx supports. Onyx can help to bridge, but in the cloud, right? So you have your AI workload, and Onyx help you to map the workload into the operations that need to be done on the hardware. But in the cloud, you need to figure out where those hardwares are. You need to figure out where to find the right hardware for the right workload. And they can be, those hardware can be anywhere in your data center, and they could be various different hardwares. We need to ask the right question. Can we have an AI cloud infrastructure software which provides a nice abstraction and management of the heterogeneous resources, and is open source and driven by open community, and it facilitates the end-to-end AI development workflow? Now, that brings us to the next topic, is the Cyberwar. So Cyberwar is a general management framework for accelerators, or as I said, DSAs, domain-specific hardware. And it's an official project in OpenStack and is funded in 2017. I'll just briefly go through what Cyberwar can offer to the ecosystem. It can discover heterogeneous resources, DSAs, and manage the runtime libraries and packages, access quota control on the resources, works with devices from various vendors, and standardized API for resource management. And you can, for FPGA use case, you can program your FPGA bitstream through an API portal, and it works with node placement to schedule the resource for the VMs. Now we have Cyberwar and we have Onyx, and we try to close the loop here. So Onyx plus Cyberwar, what it can offer. Onyx provides a high-level intermediate representation of the operation that user wants to do. If you come from a compiler world, IR is probably very familiar with the 2U. It's just an abstraction of the operation, operation you want to do on the hardware. So it answers the question of what the user wants to do. And Cyberwar provides another perspective, is a resource representation, we call it RR. It answers the question of how to do and where to do it. And having these two together, IR just generates a model metadata schema, and then RR generates some sort of policy, like resource policy. Put these two together, we can fit them into our scheduler, and then we can place our AI workload into the right places. Now we close the gap. We have, on the top, we have the AI application running on AI frameworks. And Onyx helps you to map those operations, like those AI workload onto the right operation. And your cloud infrastructure utilize Cyberwar to map those operations into the right hardware and right location in your data center. And down underneath, you have all the various different hardwares that accelerate your workload. So that's it for the Cyberwar talk. And next, I will pass along to Jinghua and Zhenghao for the heart disease detection in using deep learning.
Thanks, Lee. Now we are going to talk about the heart disease diagnose platform using deep learning. At first, we will introduce the medical background. Then we will talk about the scenarios using deep learning to diagnose heart disease, both in the edge and in the cloud. Next, we will focus on our edge platform, how our edge platform to satisfy the real-world requirements of heart disease diagnosis in rural areas. This part, we are going to introduce the current status of heart disease and how deep learning benefits the healthcare, as well as the challenges using deep learning models in the heart disease diagnosis in rural areas. According to the World Health Organization, cardiovascular disease, or we call it CVDs, is the top cause of the death worldwide. And in 2015, over 30% of the global deaths were due to CVD, leading to over 70 million of deaths, which is a global health burden. Of those deaths, there are over 7 million were caused by the heart disease, and greater than 75% of the CVD deaths were in developing countries. So as you can see in the world map, which demonstrates the distribution of CVD deaths. While mostly in the developing countries, one medical report points that the important reason is that the heart disease couldn't be discovered at an early time due to the lack of the medical resources in these rural areas. And this caused the missing of the best treatment time. In developing countries, medical resources are scarce and distributed unevenly. Like in China, we have very good facilities and experienced doctors in big cities like Beijing, Shanghai, and so on. But there are lack of facilities in the rural middle west areas, and especially the experienced doctors. Unfortunately, deep learning technologies often ways to diagnose disease automatically. As the deep learning technology evolving, it will benefit millions of people in rural areas. According to the IDC report, there are two aspects of deep learning applications. There are two aspects that deep learning applications may help. One is the clinician augmentation, and the other one is prediction of the risk of the disease. The figure in the right top identifies the journey for deep learning in augmentation of clinician, and the right down figure shows the journey of deep learning in the prediction of disease. Although diagnosing using deep learning is at a very early stage, it has got regulatory approval in some countries now recently, and this all shows that deep learning can play a key role in the near future, from improving the timeliness and accuracy of diagnosis to helping in addressing the problems of doctor shortages. We can train deep learning models based on the accurate labeled data by the experienced doctors, and then help diagnosing using the deep learning models in the clinics. And in this way, deep learning may help in solving the rare and uneven distribution problems of medical resources. To make that happen, we must first face the challenges of disease diagnosis platform when using deep learning models. The first challenge came from the deep learning applications and the models which are usually evolving fast. And the second challenge is the clinics are located in different separated locations. And the third one is the lack of maintenance expertise in hard deployed environment. And the fourth one came from the performance improvement requirements of inference and training, which required dedicated hardware. To cope with these challenges, we came out a diagnose platform, which is an edge platform, and it enables hardware acceleration, workload optimization, and edge cloud collaboration using deep learning models. And before we elaborating the edge platform, let's see the scenarios using deep learning models to diagnose heart disease, and what's the deep learning algorithms in the edge and in the cloud. Using deep learning to diagnose, there are two-step process. First, in the remote clinics, we do the preliminary screening for heart disease using the coarse-grained deep learning models. If the preliminary screening result is normal, which means that the users don't gather heart disease, it will return the result quickly. But if the result is abnormal, then we will need the second step. By sending the abnormal data back to the cloud, we can do classification using the fine-grained deep learning models. The reason we are going through these two steps of disease diagnosis, for one thing, is to reduce the amount of data sending back to the cloud, and for another thing is that the edge may don't have the great capacity doing the fine-grained classifications. As a result, the users in the clinics then gather specific result from their cloud. And example of these two steps of diagnosis process is in the edge, we predict whether one has the heart disease, and in the cloud, we predict whether one has the premature ventricular contractions, or we call it PVCs. It's a kind of the heart disease. Involving the deep learning models, we should go through the dynamic training process. It can help improving the diagnosis accuracy step by step. In the edge, we collect the data and send it back to the cloud. And in the cloud, we retrain the model once we got more labeled data from the doctors. And this will help evolving the models towards a more secure, a more accurate one. About the data, in practice, the abnormal data may contribute more to our models evolving. So we send back all the abnormal data as well as a small amount of the normal data. This will help reducing the amount of the data transmission. And now let's see the ECG algorithms, which is used to predict and classify the heart disease. In the edge side, we have deep learning models to do preliminary screening. The edge side application enables data normalization and denoising, signal quality assessment, QRS waveform detection, adaptive filtering, abnormal, normal ECG signal detection. And in the cloud side, we have the deep learning models for classification. The cloud side application has the entire processing of the ECG algorithms, which is shown in the right picture. Also, we can recognize different abnormal ECG signals like PVCs, supraventricular premature beats, and atrial fibrillation, etc.
Okay, let's start my part. I will introduce the edge platform in this part. This section is the architecture of the Think Edge platform hosting medical applications. I will introduce in several features of the platform and gradually extend to overall architecture of the platform. The first is cloud edge collaboration. which consists of 2 layers. First layer is Cloud Edge resource collaboration. Macro analysis applications need to be deployed in both the cloud and the edge to support business requirements. We deploy the classification application in the cloud Kubernetes through the head-based orchestration tool ThinkCloud Orchestrator. And it also calls the cloud adapter to push the deploy requirements to the edge to deploy the preliminary screening application. The compute, network, and the storage in edge can collaborate with cloud to deploy a complete medical diagnostic application. This is a typical cloud edge resource collaboration scenario. The other layer is cloud edge data collaboration. In the business process of disease diagnosis and the dynamic training process, we can easily find that there are frequent data interaction between the cloud and edge. In the cloud edge ecology of Lenovo, the cloud adapter component is responsible for data exchanging. From the previous description, we can easily conclude that cloud edge collaboration is mainly done by cloud adapter, which is specifically responsible for 2 things. For the edge side, it is syncing cloud-side resource updates to the edge and reporting edge-side host and device states changes to the cloud. For the cloud side, it is watching changes at the cloud side, catching and sending messages to the edge-side cloud adapter. The second feature is application acceleration. The ThinkEdge platform can use acceleration accelerate the AI applications. Currently, it supports GPU meridians and so on. On the container aspect, DPI is currently used for designated resource extension. In the future, we plan to use a Cyberwar project to unify heterogeneous acceleration hardware for the platform. Another feature of the ThinkEdge platform is workload optimization. Look at the graph here. It shows the process relationship between the monitoring and the workload optimization. There are 2 modules, resource pool, monitor stack, alarm, and action control plan. Resources in resource pool include virtual machines, container pod, load balancer, bandwidth, and so on. The monitor stack is a collection of monitor systems, including Prometheus, Ceilometer, and Lenovo self-developed ThinkNet. Alarm and action control plan, as the name implies, we don't need elaborate too much here. The overall idea of the whole system is that the monitor stack monitors the key indicators of a deployed application. After processing the monitor data, the static and predictive rules are determined and then sent to the control plan to make a corresponding workload adjustment. This may be too abstract. Let me show a concrete example. This slide shows a specific scenario to illustrate its workflow. First, we will select a virtualized template and auto-deploy it in ThinkEdge by one-clicking the web app, which consists of load balance node, web server node, database cluster, also includes related monitoring resources and linear regression model, and so on. Then the Ceilometer will start to collect the request rate of the load balancer. Third, send simulated requests. And finally, traffic burst lets AODH execute alarm action. Hit CFN API to scale up for the stack. Of course, there are other configurations to prevent abnormal conditions such as jitter. In order to save time, it will not be elaborated. We have extended the AODH. If you choose the prediction type rule, you can use a pluggable predictive model to analyze the monitoring history data. And finally, provisioning resources ahead of the traffic burst. Okay, there are some of the features in the platform that I want to share with you. Then let me make a quick summary of the architecture. This slide is the platform overview of our solution, including 4 layers. First of all, let me talk about the hardware layer. In this production, we used server supports several USB interfaces so that we can plug narrow compute sticks, also known as NCS. For now, we have already supported the 2nd generation NCS. About the infrastructure management layer, we deploy our solution based on Kubernetes platform. With the help of Kubernetes, we can not only deploy our solution quickly and efficiently, but also make it easy to be monitored. In this platform, we use Cloud Adapter to transfer data between edge and data center. This is the service layer. And at the top of the architecture diagram is the APP layer. Okay, that's all. Thanks for your attention. And Lee, please come back to the stage.
Oh, so any questions about maybe Cyberwar or heart disease diagnose?
Hello. In the previous slide, you were showing Movidius. So it's used for the edge side, for which use case with which machine learning algorithm? Movidius, you have shown a
This one?
This one, Movidius, so it's ASICs. So,
so let me see. So you're asking about the algorithms in the running on the Movidius,
yeah.
Right? Okay. So we are doing the abnormal and normal ECG signal detections, which is running on the Movidius. Yeah, and about the details of these algorithms, I may not know quite specifically, but if you are interested, I can send you an email about it. It's done by my AI team. Yeah.
So because Movidius are more used for IoT, for small devices, and you are using Movidius with servers or
是说你这个 Movidius， 他说一般是用在 Edge 对吧？他说是说为什么你是用到了server 上，还是说跟他 clarify 一下，这是用在 Edge 上。I think the device is actually using at the edge side, not on the server side, right?
Yeah. And it depends on what's your hardware in the edge side. Here we are showing its server, but you can maybe use a laptop, anything.
Okay, thank you.
Thank you.
Thank you.
Hi. My question is not really related to the architecture itself, but more about your data. So you're giving the example of ECG data, but what other data are you using? Do you also use, I don't know, other health data gathered on the patients?
Oh, you mean the data to?
What do the hospitals provide to your framework to feed the deep learning algorithm?
Yeah, we have the hospitals, which we have the cooperations with some hospitals in China. it's a maybe 301 hospital named 301. Yeah.
Okay, but it's not only ECG data. No, you must have also a lot of things like.
Yeah, you mean
how tall the person is, how often they eat, what kind of food, or etc. Do you also process this kind of data?
Yeah, we have the adaptive filtering or signal quality assessment before we are training the data.
Okay. Oh, okay.
Well, I think the ECG data is better for modeling for now. I think that's probably the primary data that feed into the model. Because it mentions the CNN here, right? That's probably better feed for the ECG data.
Yeah, yeah, for this particular model, I was more curious about all the other models you may have, and maybe if you had some other applications than ECG.
就除了 ECG data 之外，你们还用什么别的 data 吗？除了 ECG data 之外，你们还用什么别的 data 吗？
Right now we have the sound heartbeat data, which heart sound data. It's a sound data. Also can identify the heart disease, plus the ECG data.
Okay, thank you. And also, sorry, another question about the privacy. How does that work? When you receive the data, does it still have the name of the person tied to it, or is it anonymous? How do you treat that?
Oh, you mean the data? I think right now it's privacy. Yeah.
Probably anonymous data.
It's anonymous. Okay.
Must be anonymous.
Thank you.
Any other questions? Great. Thank you.
Thank you.
Thank you.